Hello, everyone. Welcome to my talk. Thank you for being here. Ever since I talked about how to rangify your code, people asked me about the performance of the ranges. And in my last talk, I benchmarked the code a little bit, but I didn't go into detail into the performance of all of this. And so I thought it might be interesting to use some tools and try just to analyze the ranges code a little bit. And so here we are. So this talk is an outline. I'm first going to start by telling you how the setup is, so how I generated my results. Then I'm going to show you a code example. And because we need to compare the ranges output to something else, I wrote 3 versions of the code. The one that I called C-style C++, where I don't use any standard library stuff. I have the C++ 17 version where I use stuff from the algorithm header and algorithms from that, and also standard containers. And then I have the C++ 23 version where I use mainly ranges. And with ranges, in this case, I mean mostly views. And I'm going to analyze all of the 3 versions or compare them, first using Google Benchmark, then CacheGrind and the Visual Studio Profiler. And the profiler will be a live demonstration. Scary. And so I used the Visual Studio Profiler before, but I'm fairly new to the Linux tools because I am a Windows developer, always have been. I grew up with Windows PCs. And so for you, the experience might be the exact opposite. And after we looked at the output of the tools, we are actually trying to optimize all of the 3 versions of the code. And then we run the tools again, and in the end, compare all of the results. So let's first start with the setup. So as I said before, I'm a Windows user, and I always have been. So also at work, I mainly develop on a Windows machine and also use Windows compiler. And so I never really had the inclination to learn Linux or the Linux tools. So I wanted to have the setup as easy as possible for me in order to use the Linux tools. That's why I used a WSL. That's the Windows subsystem for Linux, which is a virtual machine that runs on your Windows computer, and it installs Ubuntu on default, and then you can use it like a Linux computer. And the nice thing for me is that I can access all of my files that are on the WSL from the Windows, and also the other way around. So the drives are mounted to each other. So that makes it actually extremely easy to use, especially for me. And what also is interesting, the computers that I'm using. So this is my laptop. And we will run the Visual Studio Profiler on this laptop because I don't have anything else here. And as you can see, it's not built to do any kind of hard work. It's hardly built to do any work. That's why I need a new computer. I'm saying this for a while now, but I really need a new one. But I also, of course, have a main PC, and this is my ridiculously overpowered gaming PC, which I love. It's super fast, and as you can see, it's a huge difference between the setups. And this is where I generated the CacheGrind output and also did the Google benchmark on. So that you know if the profiling result looks a little bit strange, it's because I'm doing this on this laptop. So now we have arrived on the code. I wanted to find a real-world example where I can use as many ranges and views as possible and compose them all together. But it turns out that's actually pretty hard to find. And so I just made up some code. I made up some nonsense code where I use as many different range adapters from C++ 20 and 23 as possible. I'm going to show you the code. I'm not spending too much time on the code. It's not meant to make sense. It's meant to be compared for the output. Like in a real-world application, you would have a mixture of all of these probably, but now I wanted to have like a pure output of the ranges and the algorithms and the C-style C++. So don't worry if the code does not make any sense. It's not supposed to. Just wanted to put in all of the features that I found. And in order to mimic some kind of real-life functions, I made 3 sub-functions, and in the end, one function that calls all of them. If you're, I don't know why, but if you're interested in the code, it's on my GitHub. So you can look at it later and even look at the optimized version. I will say it later again. This is only after 1 cycle of optimization. So if I would be really out to do as high as performance as possible, I would not stop here. So I would do more optimizations. This is just where I stopped for the talk. And also, so the first versions that I show you is what I would write naively without caring for like any performance. So again, as you know, you should only just optimize your code if you know it's too slow. If you benchmarked it, you know it's too slow, then you should start to optimize it. So at the stage where you first write the code, there's no reason to like try to optimize everything from the beginning. So I'm going to start with the C++23 version. As I said, I wrote 3 sub-functions. This is the first one. And so this function takes a standard vector as input. And then I'm going to use one of my favorite views, which is the Cartesian product. And what this actually is, it is a nested loop. So it combines all the elements of all the ranges that you put in with each other. And so this first range that you input is the outermost range from your nested loop. Then the second one is, in this case I'm using 3, is the one in the middle. And the third range that you put in is the innermost range of your nested loop. So this is a nested loop of 3 containers. And as you can see, I'm just using the input range and modify it a little bit for the innermost range. So Cartesian product, as I said, is a view, and it creates a view of all of these combined elements. So you get references to all of these elements, and you get a tuple with these references that you then can address and do something with the values. So that means at the end of these parentheses here, we're not doing anything. We created a view, but I mean, it's called Cartesian product. You might think there's like some computation there, some multiplication because you get a product. No, it's just a combination of all of the ranges. And then you need to do something with it. So I call transform. Transform gets a tuple of the references of all the elements. I love structured bindings, so I always use them. I hate the get syntax. And then I just do something with the values. Again, it does not have to make sense. I just need to use all the values in some way. And I'm going to return, as you can see, I'm going to return this view. And when you were in Nico's talk, and also if you know ranges, you know that this does not execute anything. Ranges are executed lazily. So we can return this view here, but it will only be executed once the value from this view is needed. So once we call the star operator on the first value of this range. And if you want to write this function in C++17, you have no other option than to actually use a nested loop. I love to create vectors and then return vectors in the end. So this is what I'm doing here. So I need to have the result stored somewhere. It's not like the ranges view where I have all of this in a lazy way. And so I loop over the outer range, the middle range, the innermost range, do the calculation. This is the calculation that we did before in the transform view. And I push back the element that I calculated, and then I return the vector in the end. So this is the exact same code than before, just written in a different way. And of course, we have C-style C++. As you can see, it's C-style, so I'm using pointers, and because it's dynamic memory, I need a size for my range. I have a new in there, which is super scary. And then I need to use indexed loops. As you saw before, I used range-based for loops, and now I'm using indexed loops because I'm in the C-style world, but the calculation itself is the same. And here I'm returning this dynamic array from the function, which I need to remember later because I need to delete this. So the second function is a short one. I really, really wanted to use zip-with, which is called zip-transform in a standard library. And I haven't told you that this stuff is completely implemented in MSVC currently, but one crucial function is missing in GCC, which is ranges2. This is why I'm using range3 here and not the standard library. I would love to do this with the standard library, but I'm using just this one. I'm needing this one feature from GCC, which is missing. So that's why I'm using zip-with here, which is called zip-transform in the standard library. And zip-with combines all the ranges that you input, and you step through them like at the same time, in unison at the same time. You have to put the function first for zip-with because, for internal reasons, this is it takes a parameter pack for the ranges, so you can input as many ranges as you want, but then you need to have the function at the first as the first argument. It's not that pretty, but it's the language. And then you input all your ranges that you want to combine. Again, here I'm returning the view. No work has been done yet, nothing has been executed. It's the instruction that we're returning here from the function. Doing this in C++17, we can use std transform. Again, it's the C++17 version, so there's no range-based version yet of the transform, so I'm using the iterators. And I'm doing everything in the transform that I did before, also in the transform view. But I'm returning a vector here. And for the C-style C++, you know the drill. Get some memory from the heap, have an indexed loop, do your calculation, and then return your memory. And the third function, we're almost done. The third function just creates two temporaries here. I use partial sum because I like it. And for the second temporary, I use the sliding view also because I like it. I think it's very common that you want to use something like that. And then I, again, just do something with the values. I always call them transform on my views and then do something with the values. And in the end, I wanted to have one output. And to get one output, I'm using inner product, which gives me one double in the end that I can compare that I'm actually doing the same thing for all of the versions. And yeah, that's basically it. So because I'm using the sliding view for the temporary 2 view here, I'm getting one element less than I get from the input range. So I need to drop one value, which is what I'm doing in the inner product here for the first range. Again, it's nonsense code, but it uses a lot of features, as you can see. So we can actually write this quite nicely in C++17. All of this has an algorithm in the algorithm header. So I'm using partial sum, as before, with the ranges. I'm also using here adjacent difference. Which is actually quite nice. It is a terrible name for this algorithm because with adjacent difference, you can do anything to the adjacent elements. You don't have to calculate the difference. That's the standard behavior if you don't put in any other function. But you don't have to use it. So you can do anything with the adjacent elements. So this is what I'm doing. I'm giving it a lambda, and I'm just doing what I want. So name is terrible, function is great. And then I'm calculating the inner product, and also like a need to shift the iterators a little bit because also for the adjacent difference, the first element is not what you want. So the first element is not the result of the calculation, it's the first element of the input range. So you typically don't want to use it. I actually don't know why they did this. It would be very easier to have like the last element be different, because then you could just cut your range at the last element. If you cut it on the first element, then you need to copy all your data in memory, and everything is bad. So for C-style, we of course don't have any algorithms here. I should have used some comments in order to make this a little bit more readable, but to have it like fit on the slide. This is the partial sum. This is the thing with a sliding view with the two elements. And this is the inner product. And in the end, we need to delete the two temporaries that we just created. Nothing goes wrong on this point, so we will actually reach the delete. So again, this is just a very quick overview over the code. If you really, really want to look into this in more detail, it's on my GitHub. You can get it later. Yeah, and in the end, of course, I return the sum. And so the last function is just calling all of them. So the first function I call with the input range that I get overall. The second function I call with the result from the first function. And then I call the third function with both of these temporary results. Same with C++17. Note that we could make these const in the standard library, those ranges, but it's non-const in range v3. I actually don't really have an answer for that. I guess Nico has. Yeah, and doing the same with the C-style, but then again, we need to delete all of our temporaries because it does not do this on its own. So the first tool that I'm going to use to compare these three versions of the code is Google Benchmark, because Google Benchmark is a platform-independent tool, and it's extremely easy to set up and use. And I can compare all of the three versions of my code at once, which is also really nice. So to use Google Benchmark, you have to implement one function that takes a benchmark state as an input parameter. Then you prepare all your data or your input that you don't want to be benchmarked. Then you have a for loop over the state. And in this for loop body, you do the thing that you want to benchmark. I'm using do not optimize here from the library because compilers are kind of intelligent. And I'm calling a function here that returns a double that is never used anywhere. And so it's a high probability that the compiler optimizes the entire function call away because I'm not using the result anywhere. And do not optimize prevents that. So it actually executes the function that you want to benchmark. Then there's this macro where you have to register your benchmark for in order to be executed. I changed the output here to milliseconds. By standard, it's nanoseconds, and it's just a huge number, and I don't think it's very readable. So I like milliseconds here. And then there's a benchmark main, which is also a macro, and then it calls all of the registered functions and calculates the benchmark for this. So this is the entire setup. I think it's super easy, super fast to do. And then you run this. So you run your program, and then you get some output. And so the first number that we have here is for the C-style, and it actually runs for 25 milliseconds. Then we have the C++17 version, which is a little bit slower with 35 milliseconds. And then we have the ranges version, which is super slow. Something happened there. Don't worry, there's actually a problem in the code. We're going to fix it in the optimizing round, and then we'll benchmark again. But this is an error that is not easy to spot, I think. So we will see this then in the optimizing round. So next, I thought I look at cache grind, because why not? So while grind is around for I don't know how long, and I never really looked into this. I mean, why should I have? And CacheGrind is used to do performance profiling and analyze and optimize the cache usage of the program. So I never saw this like in any talk that someone like analyzes the actual cache usage of the different versions. So I thought I'd just do it. And then, with the output, we can try to optimize, or we can try to see bottlenecks in the cache usage and try to optimize that in the program. So if you never used CacheGrind before, you will be a little bit overwhelmed by the output that you get. So I'm going to go through the output like line by line, just that everyone knows what we're talking about here. And so if you run this, you get this kind of output. I mean, CacheGrind is a command line tool for Linux systems. If you run this, you should build in release mode, so optimized, but with debug symbols, especially if you want to analyze it any further, because without debug symbols, you cannot read the additional output that CacheGrind produces. So the first block is the instruction cache statistics. An instruction cache contains all of the instructions of the program. When the processor needs a construction, it first checks the level 1 cache, which is the fastest cache. And if the instruction is found in this cache, then it's called a cache hit. And if it's not found in this cache, then it's called a cache miss. And then it may have to be fetched from memory. And this is what makes your program slow. So everything that runs in the caches, especially in the level 1 cache, is super fast. And the further up you go in the cache until you reach the main memory and or the hard drive, then it gets super slow. So that's what you want to look out for when you're looking at this output. So next we have the cache misses for the level 1 cache. And then we have the cache misses for the last level cache. In my case, I have the level 2 and 3 cache combined here in the last level cache. And then it shows you also a miss rate, which is in this case 0%. I call this pretty good. And then we go to the next block, which is the data cache. And data cache is quite similar to the instruction cache. It contains all the data that your program needs in order to be executed. So data that you access frequently will be in the level 1 cache, and data that you don't access frequently will be stored far away in the caches, like in the higher level caches or on the main on the hard drive, in the main memory. So if the process needs to read or write data, it first checks in the level 1 cache. And if it again finds the data there, it's a cache hit. And if it doesn't find the data there, it's a cache miss. Also, CacheGrind shows you the read and write operations separately as well. Again, if it doesn't find the data in the cache, it needs to fetch it from main memory, and this takes time. So you always want to have your miss rates low. And then you get the percentages again. So in this case, we will go over the numbers later. So in this case, the cache misses are actually quite high. And then the next block is the last level cache statistics, where the last level cache combines the level 2 and 3 cache here on my computer. And it refers to the highest level of cache in a multi-level cache hierarchy, which is what you all have in modern processors. And it also it contains the data cache and the instruction cache. And this also plays a crucial role if you want to optimize your program, because the more data you can do in the higher level caches, or lower level caches, sorry, the faster your program is. And then in the end, we get also statistics about the branches that were created in the program. It's split into conditional branches and indirect branches. where conditional branches are changes in the execution flow of your program. This happens in for loops, in if statements. So every time you have a condition, then you create different branches, and then you jump according to the output to those different branches. And indirect branches are jumps in the address of the register from the memory location, and this happens for like function calls, virtual function dispatch, jump tables, and all of the situations where the address of what you're calling is not known at compile time. And so the next lines indicate the branch mispredicts that are occurred and then the miss rate. A branch misprediction happens when the processor's branch prediction mechanism predicts the wrong branch outcome. And mispredictions are bad for the performance of the program, because that means that the program fetched the wrong instruction and has the wrong instruction in the level 1 cache, and it cannot use this instruction. It has to throw it away and get the correct instruction. So this is also what can make your program slow. So we haven't really looked at the numbers yet, but I will compare them shortly with all of the versions. So you don't need to remember all of the numbers that I just showed you for the C style. This is here to have the slide deck complete. So if you get the slide deck later on and you want to look at all of the numbers yourself, you can do this here, also for the C++23 version. But what I'm going to show you is the comparison, because even I can't remember all of these numbers. So as we can see in the first row, that the C style C++ version has the lowest numbers of overall instructions created, and C++17 is in the middle, and C++23 is actually quite high. What I found interesting is that the total number of misses are the same for all of them. And but miss rates are 0 for all of them. So it may not be a problem. So just because you have a lot of instructions doesn't mean you have a problem. If the miss rate is high, then you have a problem. Also for the data refs, same direction here. What is interesting to note is that we have very, very low data misses in the ranges version. And that's because for all of the other versions, we created temporary vectors that live somewhere in the memory. And they have to be stored somewhere, they have to be written, and they have to be fetched again if you want to read it. This does not happen for this version of the C++23 code, because once you request one of the values that in very low than in the inner product, where you actually use all of the results that you want to create, then it fetches the memory from your one input source. And that's actually quite good in order to manage all the data caches, because you don't have any additional memory stored that you need to fetch. So you only need to fetch this 1 or 2 values that you need for the actual execution of the algorithm. This is why the number is so low. And also, I said before, the miss rate is super high. I think for the C style C++, I don't have that much of experience, but just looks like a high number. And so last level cache also is very low for the C++23 version, which is the same reason than we saw with the data refs. We just don't need to do this much stuff in the caches, because we only have this one input range that we are using. And we only need to access this and then do all the calculations in place. Branches are quite high for C++17 version. This does not have to be a problem as long as the mispredicts are low, and they are almost the same number again for all of the versions. And but it's not a problem unless the mispredicts are high. But it's just something that I noticed. So this is what I would focus on just by looking at this output and trying to lower these numbers. So now for the fun part. We're going into the Visual Studio. And we use the profiler. Has any one of you used the Visual Studio profiler before? Oh, quite a lot, actually. That's good. So in order to use the profiler, I mean, you can use it with almost anything. As you can see, you can use your startup project, which is a Visual Studio project in my case. But you can also attach it to a running process, an executable. Oh, sorry. How do I get this? Wait. This is not working. Wait. We will get this. Yeah, I think so too, yeah. Oh, what's happening? Is there any tech support here? Ja, ich habe es gerade neu attached. Warte. Ja, ist das auf dem anderen Monitor? Ja, ich muss duplizieren. Ja. Better? Okay, so yeah, I just wanted to show you, yeah, you can use your profiler with your startup project, which is in this case a Visual Studio project, because I think it's the easiest to use, but you can attach it to a running process, an executable, running app, like anything probably, and it also works with CMake projects. I'm going to use the CPP usage. I'm not looking at all of the other tools. I'm building in release mode and x64, and I'm just hitting start. So this is all the setup I'm doing for the profiling. You can do this, computer. Perfect. And then once you started the profiler, you get like this top view of the diagnostic session with some kind of statistic here, where all your execution of the C++ stuff is actually in kernel, because we don't really have any runtime that we need to start. Like in C#, you have your .NET runtime that also does a lot of stuff and memory management, and we don't have that here. And I'm always just clicking one of these functions here, don't really care. And I'm going to go to the flame graph. So I also don't really care for these ones. I want to use, I want to see where the time is spent. So I like to use the flame graph. And there you can click into your program, and it highlights where you are in the program and how much time we have spent in that function. And then also the size of these thingies is according to how much time we spent in the function. So I'm not really spending too much time here. So of course we spend a lot of time in the loop. This is what is expected. Also for the second one, well, we're in the loop. Nothing interesting here. And we can see we spent the most time in the third function, where we have these two temporaries, and there we spent the most time in the first function. If I wanted to optimize this, the profiler doesn't really give you any hints on what to do now with the results that you get. So you need to have some like optimize techniques in your head already, or you need to learn them. And so for this version, what I would do to optimize it, and what I'm going to do is, I'm going to get rid of the 2 temporaries here and combine all of the 3 loops into one loop, because I'm iterating over the same data like all of the time, and I really only need one loop for this. So this is what I'm going to do then with the optimization for the C-style. And this is then the first round of optimization. Then, of course, you can go back and profile again and see where you spent the most time and try to optimize the next bit of code. So if we do the same for the C++17 version, we can actually do relaunch performance profiler, which will launch the performance profiler with all the settings that you did before. I mean, we didn't do any settings, but it just saves 1 click. It's nice. So this is how the output looks like for the C++17 version. Again, not really spending too much time on this overview here. I'm also not using this like extremely regularly. And again, I like to look at the flame graph. And wow, we can see we spend most time in main. That's interesting. And here we can also see that we spend, again, the most time in the third function, where we have the same problem that we have in the C-style version, that we use like these 3 algorithms, which are loops in the background, and we could combine this into one. It will lose a lot of readability, because this just tells you step by step what you want to do, but you will lose readability if you move it into one loop. But I mean, it's the trade-off. If you're interested in the fastest code, then you will lose some readability. That's a game. Yeah, so we look at the same. So now this is actually the interesting part, because this was the slowest function. So now let's see if we can spot something in the profiler and see where we spend all of our time. Yeah, that looks fun. So let's click one of these. Again, look into the flame graph, and as you can see, you see nothing. Again, we're in the main function. This is what I expect. And then if you click here, this is some memory address. We are in range v3 numeric inner product, which also makes sense because all of the work that we're actually doing, everything that we're executing, is in inner product. So before we had all the views which are not doing any work. This is the feature of ranges that are executed lazily. And inner product is the first point where these values are requested, and that's why we spend all of our time in inner product. So that makes sense, but it doesn't explain why we're this slow. So we're still in inner product. We are in basic iterator, which I think is called by inner product. So this, we're in invoke. And what is, well, hard to read, because this is the type. yeah, no, does not help me like even a little bit. Where in tuple algorithm does not help me again. Then here you can see the really readable type again. The only thing that I'm noticing here, well, is the Cartesian product. So it's like all of the combinations of all of the views that we did. Okay, I'm going back to main. Maybe there's something here. We are in tuple algorithm again. Yeah, I cannot work with this. I don't know about you, I cannot work with this. I cannot tell you why my program is slow by looking at this output. So I defaulted to something that I usually don't do, and I did this diagnostic session in debug mode in hopes that the debug mode doesn't optimize away this much. You will get a warning from Visual Studio, like not an angry warning, but you will get a warning that the results are not reliable if you do this in debug mode. And I prepared this beforehand because you can see it takes 4 minutes on this computer, and I don't want you to wait for 4 minutes. So let's see if the debug mode helps us a little bit. It's a little bit better. So, I mean, it at least shows you some of the functions, but again, it's also not super accurate as you can see. So we actually spent all of our time here and not at the destructure of anything. Yeah, but now you can see like way more things, but we are still all in range v3. And we don't know where the actual time is spent. Like we cannot see it like clearly. We see that we spend the most time in inner product. Again, this is what we suspect. Now we actually see it here in the output. And then again, if you just click through, we are in inner product. This is expected, inner product. And then you have like all of these locations again, basic iterator, partial, this again is basic iterator. So I still think that's extremely hard to use. So, but how, I optimized this code, but how did I get behind what I needed to optimize? And for me, it is just the type hints. So in this case, I saw the Cartesian product here at the very top, and I saw it again here, and I saw it here, and I saw it here, and like all the way down. So all of the branches that are executed in my code are calculating the nested loop, which is like really costly. Like you have a nested loop over 3 ranges. This is really costly. So I thought to myself, how does this happen? How does all my code like execute the Cartesian product over and over? And that's actually a problem in the code. And let me see. Yeah, I'm going to show it to you later in the slides. So that's actually a problem in the code. We're going to fix this. This has a reason. This has a good reason, but we're going to fix this. So now let's see. Yeah, it works. So now we are optimizing this. As I said, for the C-style version, I just want to move all of these 3 parts that I created here with the temporaries into one function so that I don't have the temporaries. I have less data that I need to store, I have and address, and also just 1 loop instead of 3 loops. So it should speed up the entire process. And you need to trust me a little bit. I cannot go into like the details of this. You need to trust me a little bit that this part is here in the shorter version. The second function, which is like the sliding thing over the 2 elements, went over here. And the third part is the inner product, which went over here. So again, the code itself is not that important. I just moved all of the loops into one. And I did the same for the C++17, but because I don't like raw loops, I used accumulate and did all of this in the accumulate, in the lambda of the accumulate. So this is the exact same thing that you saw before, just wrapped in accumulate. And now the interesting part, I think, is optimizing the ranges version. And what we can see here is that we create the range 1 here by calling the first function and then putting that into the second function and the third function. And so the second function now depends on the output of the first function. And now I'm inputting this into the last function. So now I have two separate functions where I only have the instructions how I want to calculate the values. And both of those contain the Cartesian product. And this is the problem. So I'm accessing both values. And in order to for it to execute this, it needs to evaluate range 1 with the Cartesian product and range 2 again with a Cartesian product. And this is what makes it slow. And this is, I think, something that can be easily overlooked. But it can be optimized. And I optimized this in a very easy way. I need to force this code to be executed and stored somewhere. This is, I needed this to be only executed once. So I use my favorite feature, which is range 2. And I store the output in a vector. Note that I don't have to change anything else of this function or any other functions because the way I wrote this code. I'm returning auto here, so now it does not return a range anymore, it returns a vector. It just works. And the other function uses, I think it's only auto as input. And now it also just works again. So I should have constrained like the auto of the other functions. But I don't. So this is all the optimization that I needed to do. So now let's run the Google benchmark again. Let's see if we improved. So for the C style C++, we actually doubled the speed. It's quite good, I think. Same for C++ 17. It's still slower than C style, but also performance is doubled. And yay! My ranges version is now super performant, which I like, of course. So I also did cache grind again, just to see if anything like changed for the output. I don't expect you to remember the output that you saw before. This is, again, if you want to get the slide deck, you have all the numbers. But here I'm comparing the optimized to the non-optimized version. Instruction refs went down. Miss rate is still 0. Cannot get any better than that. The data refs also went down, which makes sense because we have 2 less temporaries that we create and need to write and read. So that also makes sense. The miss rate is still high. Not an expert in how to manage this memory, so might be a trick to this. Also last level cache went down, so again it's the same reason because we have 2 temporaries less and we do all the work in one loop for the last function. And so we need to read and write less data from memory. So this is what speeds up the program. And also branches went down, so I simplified the program a little bit. Still mispredicts a 0%, so good program. This is the output for the optimized C++ 17 version. And if we compare it, we see again that the instruction refs went down a lot. Also mispredict is 0%. We also decreased the data refs, which again is the same reason than we did for the C-style version. We have less temporaries that we need to write and read and store and fetch. So this is what makes the program faster. And also the last level cache, same reason, went down. And we also reduced the branches that we created, which makes sense. The program is a little bit easier, it's a little bit simpler. But still mispredict is not high, so it's not a problem that we have these branches. At least I think so. And now this is the optimized C++ 23 version. And if we compare that, we simplified the program a lot for the instruction caches, because now we have to execute way less. what went down is the data refs. They went down a lot, but the data misses went up. And this actually makes sense because now we created a temporary vector. For the other versions, we got rid of 2, but now we introduced 1 temporary vector. And now we need to write it, we need to read from it, and this is what increases your data misses. But still, I don't think like this rate is super high. It's of course like the percentage got up, but this is what we're living with, and also the exact same reason why we do now more work in the level 2, in the last level cache. And yeah, we also brought the branches down a little bit. And now if we compare all of these, so I have a winner for all of the categories. So C-style wins for the instruction refs. It has less refs overall. But all of them have like 0% miss rate. So for the data refs, C-style creates the least data refs, but percentage-wise, C++23 wins the lowest numbers overall. Also, last level cache, we do the least work in C++23, and branches, so the simplest program from the computer's view, is the C-style version. But again, this does not have to be a problem. So what would be next? So next I would try to optimize this again, like run the profiler again, try to optimize it again if I need it. So if this is fast enough, then I would be done here. But if it needs to be faster, then I would go back and optimize again. And then run these tools, maybe use some different tools if I'm not seeing the output that I'm expecting. And yeah, for the conclusion, I learned a lot about how to set up WSL, which I actually now really like. It's very easy to use, even for a Windows user. If you want to do like cross-platform, it's super easy to use. It's integrated in Visual Studio, so you can compile your code using WSL, GCC in WSL in Visual Studio on Windows. That's cool. There are things that you need to look out for all of these coding styles. Ranges have their traps. You need to learn them, but I think you need to learn like the traps for all of the coding styles that you're choosing. For ranges, it's not that well known yet because not a lot of people are using ranges yet. So look out for Nico's talks. I think he will explore more of these things in the future. As you saw, the performance is really good in the end, without sacrificing readability. I know readability is a touchy subject because some people think that ranges code is not readable and raw loops are super readable, but I think it's the other way around. I like to see the intention of the code. I want to see what the program is supposed to do. I don't need to see how it's actually executed. But I know this is, yeah, people look at this in a different way. Yeah, so I like the functional style of this, where you express your intent. But I cannot deny that the profiling of this code was not fun. So it does not give you any hints on what's actually going wrong. At no point in this did it tell me that it's executing like the Cartesian product multiple times. So I needed to kind of infer this from the types that were huge. If it's not that obvious, and if it's maybe not that obvious to you that Cartesian product is a nested loop and this is what it's slow, this is super hard to profile. Maybe there are better tools for profiling, or we will get better tools to profile this in the future, or some static analyzers that are analyzing these kinds of things specific to ranges. But right now, I really didn't like the profiling part. And but then again, it helps to use different tools. Combine them, use different tools, see which output you can get from which tool, how you can combine it, how you can explain your program's behavior with these different tools. And then if you need to optimize, then maybe you can see something in one tool that you didn't see in the other one. Questions?
Hi. Thank you for showcasing profiling. It's always nice when somebody struggles it instead of you. I'll just mention one thing. So I think you were trying to intuit what those counters mean and why the issues occur. I might be wrong, like I was half asleep, I'm sorry. But if you want to really understand it, there is this person, Denis Bachwalov from Intel, who does trainings. He has a book and has 1 million things. Goes a lot into what does it mean to have a branch mispredict and all of that stuff. So I think if you're interested, you'd find that useful.
Yeah, that's super interesting. As I said, I'm new to these tools, so I learned the tools with this talk. But also the talk is not about cache grants, so I could not go into too much detail also for this.
No questions from the online.
Okay, so if there are not any more questions, thank you for coming. Have a nice evening.